the oblique collisions between two or more rigid bodies, we are going to apply our knowledge on the previous sections by solving this next example. So let's look at example 1. In a game of snooker, the cue ball, which is the one labeled with the color black, moving with a speed of 2 meters per second towards the red ball B here. Yep. Okay, hold on. This is the cue ball, and then this is the red ball. Right? Now the cue ball is moving at an angle 60 degree to the line of the center of the two balls. Now both balls are smooth, so there is no rotational effect here, and both of them have the same mass m. Now the coefficient of restitutions between them is 0.5. We need to find out the velocity after the collisions. So here we can represent the situation before and after with these two diagrams. Now it's always a good practice to write down the vertical and the horizontal component before collision. The red ball initially was at rest. After the collision, now the cue ball would have a horizontal velocity u and then vertical velocity of 2 sine 60 degree because there is no change in the vertical velocity. Whereas object B, this is A, object B would have a velocity, a horizontal velocity v, whereas the vertical component of the velocity after impact is supposed to be the same as before, as in this case it's 0. Right, now, once we have all the informations set up, we are going to solve this using both conservation of momentum and Newton restitutions law. Right. Let's start with conservation of momentum. Right, now, by using conservation, I will write that down one more time. Conservation of momentum. Right. So we can write this down as m2 cos 60. Now, as usual, I'm analyzing the momentum, the horizontal component of the momentum itself, because there's no vertical component of the momentum. So here we have mu plus mv here. Right, now that's our first equation that we can obtain from the conservations of momentum. Now we try to simplify this as much as possible. So from here we found that we can rewrite as uv equal to, because cosine 60 is half, so we end up with 1 here. Now that will be our first equation. Now next we're going to apply Newton restitutions law. Newton restitutions law. Right. Also considering the horizontal component during the impact. So here we have v minus u is equal to the coefficient of restitutions multiplied with the velocity of separation. So velocity of separation, in this case we only have 2 cosine 60 because object B is at rest initially. So from here we will be able to obtain this second equation, knowing that the coefficient of restitution is half, so therefore this is half. That will be our second equation. Now next we're going to solve equation number 1 and equation number 2. This will be quite simple to solve using either substitutions or eliminations. We will be able to arrive to these conclusions. The V will be, let me see, is 0.75 meter per second, whereas the U would be 0.25 meter per second. Alright, now there you have it. That's how we obtain the velocity of the two balls after the impact. Right now, I need to clarify here, the V and the U is the horizontal component after the collision. So if you wish to find velocity with a more detail. Here we will say that the velocity of A after impact is given by, I will rather use this symbol here, is given by, for A, for A in this case we can write it down as 0.25, and then we also have a vertical component here which is given by 2 sine 60. Now 2 sine 60 is basically, sine 60 is sec 3 over 2. So here we will get a sec 3. Now therefore you can describe the velocity of A after impact in the form of vector. Yes, in the form of vector. Now this is the velocity of A after impact. Now if you don't want to represent the velocity of A after impact in the form of vector, you can write that down as velocity object A. You could have written down the velocity directly in the form of vector, or we could state that object A after impact. After impact, it has a speed. We can figure out the speed of the object A after collision. So the speed of object A after collision, is basically the magnitude of the vector itself. That will be 0.25 square plus 3 square root. Don't forget that. Let me try to calculate this. I remember what is the number here. Let me try to make it smaller a bit. Okay, we have, let me see, we have 0.25 square plus 3. Okay, so square root of k here will end up with 1.75. Okay, so here we can write down it has a speed of 1.75 meter per second, and then at the same time we have to identify its direction. Now you can see that from this diagram it has a direction somewhere here. This is the speed of A, and then it's making an angle alpha to the horizontal. So we can work out the angle alpha there. So alpha is given as arctangent of the vertical component, which is sec 3 divided by 0.25 there. So let me try to figure out what is the angle itself. So in this case we have arctangent, we have square root of 3, and then divide that by, divide that by 0.25. So what do we have? We have, here I'll just write it down as 2 decimal places. So that is approximately, just write as a 2 segment figures, approximately 81 degree. So this alpha is 81 degree. Now that is how we can describe the velocity of object A, either using a vector form, or you can write down its speed and direction. Now as for object B, object B is rather more straightforward because there is no vertical component that is acting on B. So therefore object B will be moving at a speed. You will have a speed of, or in this case you can write down its vector component first. So the vector representation of its velocity would be velocity of B. Here write down velocity of B is given by this. In this case it's just 0.75, and then there is no vertical component, so that would be the velocity of B. Or you can say that object B has a speed of 0.75 meter per second, moving to the right horizontally. based on the diagram that I have drawn. Right, now that's how we apply the oblique collisions between two or more rigid bodies.